So we'll do application of calculus to physical world. Okay, what's the rate of change? Rate of change is the instantaneous rate at which some quantity Q is changing. So thus the rate of change is the derivative dq dt, where t is the time. Graphically, it is the gradient of the tangent to the graph of Q. Maybe I'll just draw a graph. So you graph the quantity Q against time. Then the rate of change is the gradient of the tangent. Alright, gradient of tangent. Rate of change is the gradient of the tangent. Okay, so when a quantity Q is given as a function of time t, differentiation will give a formula for the rate of change of Q. In problems, the polynomial Q is usually replaced by a more convenient polynomial such as P for population, V for volume, and for mass. Okay, let's study the connection between quantity and rate. So if I differentiate the quantity, I get the rate. And to go backwards, we know differentiation and integration are inverse processes. So to go backward, we integrate. So if I integrate the rate, I get the quantity. After we do this, we now going to do example 1. Alright, so we'll have a look at this problem. The number of bacteria is increases according to this formula. Find the time where t is the time in hours. Find the number of bacteria initially. So initially means t equal to 0. That's when you put 0 into the formula, and you will get the initial number of bacteria, which is just 2,000. Like that. The number of bacteria after 5 hours. So what you do is you substitute t equal to 5 to work out how many bacteria after 5 hours, and you use your calculator. So the calculator will tell you something. Okay. So you get 2 times 5 to the power of 4 minus 5 squared plus 2,000. You get 3,225, 3,225 bacteria. Okay, so that's how we get the quantity. And then find the rate of increase. So you have to find, when they say rate, means you have to differentiate. Find dB over dt equal to 4 times 2, which is 8, tq minus 2t. So what you do is you substitute t equal to 5 to find the rate of increase. So you get 8 times 5 cubed minus 2 times 5. What would that be? It will be 1,000 minus 10 will be 990 bacteria per hour, because it's a rate per hour. So at that instant, the rate of increase is 990 bacteria per hour. Okay, good. So we've done this question. So it's pretty easy, this topic. So to find rate, you differentiate quantity. To find quantity from rate, we integrate. We'll look at examples where we have to integrate, but the next 2 examples, we'll just have to differentiate. Okay, we'll do another real-life problem, physical world problems. So we'll go to the next page. Okay, good. Let's move on. All right, next page, example 2. All right, cockroach plague hit the suburb of Berawang last year, but was gradually brought under control. The council estimated that the cockroach population 3 months after 1st of January was given by this formula, where P is in million. So to read the units, so P is in millions, T is in months, whereas the other one is, the other question T was in hours. So you have to read the question carefully to know what each of the pronumeral stand for. So that's the formula we're going to use. The first question they ask you to do is to differentiate to find the rate of change, which is very easy. So differentiate that, which is just 6 minus 2t. Okay, that's the rate of change of the population of cockroach. And then we're going to find the cockroach population on 1st of January and the rate at which the population was increasing at that time. So you have to find 2 things. You have to find when t is 0, the population, so we substitute t equals 0, p equal to 7 plus 6 times 0 minus 0 squared, which is just 7. So that means it's going to be Now that 7 means not 7 cockroach, 7 million cockroach, because P is in million. Alright, and then we also have to find the rate. So the rate will be dp dt. So dp dt at t equal to 0 will be 6 minus 2 times 0. That will be 6 million cockroach per month, because t is in months. So the rate will be per month. Okay, after we do this, then we're going to do the second part. When did the council manage to stop the cockroach population increasing any further? And what was the population then? So we have to stop increasing. That's about the rate, because stop increasing means that the rate is 0. So you find dp t equal to question mark when dp over dt is 0. Stop increasing. Okay, so we're going to set the derivative equal to 0. That means we'll do 6 minus 2t equal to 0. If you solve it, you get 3. So when did the council manage to stop? So that's after 3 months. So when will it be? When will it be? So remember, when t0 is 1st of January, so if after 3 months, what would that be? In March or in, when will it be? Anyone? April, yeah. So just be careful. So 1st of January, that's t0. So when t is 1, that's actually in February. And then t equal to 2 is in March. So therefore t equal to 3 is in 1st of April. Okay, so you can work out like this by counting. So you don't need to write so much. You just have to write 1st of April. 1st of April, so you write 1st of April. But we also have a second part to answer. What was the population at that time? So what you do is substitute t equal to 3 into p. So you get 7 plus 6 times 3 minus 3 squared. Use your calculator, you will get, actually you can do it without calculator, 7 plus 18 minus 9. You get 16, so 16 million. So when it is stopped increasing, there's now 16 million cockroaches. Okay. All right. After we do this, we have to find when were the cockroaches finally eliminated. That's when p equal to 0. So note the difference between when it stopped increasing, which is about rate, and then when you get eliminated, which means the quantity becomes 0. Okay. So that's when p is 0. So we get 0 equal to 7 plus 6t minus t squared. We have to solve a quadratic equation. So we multiply both sides by negative, so you get negative 6t minus 7. We'll solve this quadratic, and we'll factorize, so it will be t minus 7, t plus 6, isn't it? No, plus 1. Okay, so what that means is t equal to 7 and negative 1. But remember, t stands for time. Time cannot be negative, so therefore, you will say, when were the cockroaches eliminated? So after 7 months, so that will be 1st of August. 1st of August. Okay, 1st of August. That corresponds to t equal to 7. 7 months after 1st of January. Okay, that's when you got finally eliminated. And finally, we're going to find the average rate of increase in the population from 1st of January to 1st of April. Okay, so average rate will be is equal to the change in population over change in time. Change in time. Okay, so we need to find the change in population. 1st of April, we remember that was 16 million, isn't it? 1st of April. So you do 16 million, subtract 7 million on 1st of January over 3 minus 0, which is 3 months. So that's equal to 9 out of over 3, which is 3 million. So the average rate of increase will be 3 million per month. 3 million per month. That's the average rate of increase. Because in 3 months, the number of cockroaches increased from 7 million to 60 million over 3 months. So on average, every month is 3 months increase. Okay. So now we're going to draw all this on the graph below, which I provided you with the X and Y axis. So we're going to draw both of the graph, the rate and the P on the graph below. And then show all the information we just found. So we got P against time. This will be the rate against time. Have a try to draw them. You've got both equations. Remember, the rate is dP dt, and that equals to 6 minus 2t. So you have to draw this graph, whereas the other one, P equals to something. P equal to 7 minus 6t plus 6t minus t squared. So you have to draw a parabola. Okay, so we have to draw both. But when you draw it, you can actually use the information you found earlier. Now, what was the initial population? 7. So that means starts from 7. And what's the highest population? 16, right? After 3 months. And when was it eliminated? After 7 months. So now we already have 3 points. So you can use the information in the question. So it's maximum after 3 months, 16 million. So that's in million. So when you draw the graph, specify that's in million. And the other one is in months. Okay, like that. So we know it's a parabola, so it goes like this, goes up, goes down, like that. And the graph stops there because no more cockroach. There can't be negative number of cockroach. Therefore, I deliberately not include the negative part of the y-axis because you can't have a negative number. Okay, good. On the other hand, the rate can be negative because it could be positive or negative. All right, let's look at the rate. Now, what was the initial rate? I think it was 6 million per month. So it starts from 6. And then it stops increasing after 3 months, isn't it? That's when the rate is 0. And then finally, and then you just say straight line, isn't it? This is a straight line, so you just draw a straight line. Maybe it stops at 7, because that's when cockroach eliminated, it will stop decreasing. Okay, so that's your graph. So basically, when 6, that's really the gradient at the tangent. So that if you draw the tangent, the gradient is 6. And at this point, at t equal to 3, that's when the gradient of tangent is 0. That's when it stops increasing. The cockroach stops increasing. And then when this point, that's when it got eliminated because it's 0. Okay. What else are there? We also have the average rate for 3 months. That's the average rate. So the average rate will be actually wrong thing. Average rate was this. So that's the gradient of the chord. Gradient of chord, that equals to the average rate. So the instantaneous rate is the tangent. The average rate corresponds to the gradient of the chord. Okay, so it's equal to 3 million cockroaches per month. Okay, all right. So we've drawn the graph, so we can see in the first 3 months, gradient is positive, so it's going increasing, and after 3 months, the gradient become negative, start to decrease. So when the derivative is negative, we see the quantity is going downward. When the gradient is positive, the quantity is going upward. Okay. All right. I think that's it. All right. Any other questions? Good. So we're going to move on to the next example. All right. We'll do more problems. So the next one we have to integrate because we're given the rate. And then there's some other problem we do. We're going to do 6 pages. Yeah, there's enough time. Okay. Okay, move on. Okay, let's look at this problem. Now, this question is about rate. It says a tank contains 40,000 liters of water. When the draining valve is open, the volume of water is in the tank decreases at a variable rate given by this. Okay, so when t is the time in seconds after, yep. All right, let's continue. So this is a rate of decrease after opening the valve. So read the question carefully. T is the time in seconds after opening the valve. And V is the liters in the tank. So you have to read this question. Maybe we'll use a highlighter, so better. So V is the water in the tank. These are the keywords. T is the time in seconds after opening the valve. Okay, so now we'll go back. Okay, good. All right, once the water stops flowing, the valve shuts off. Okay, so now what we do is we'll look at the first question. When does the water stop flowing? That's when dV dt is 0. Stop flowing, it's a rate. It means that the volume stops changing. That's when the derivative is 0. So you make that 0, so you get negative 1,500 plus 30t equal to 0. We'll now have to solve for t. So 30t equal to 1,500, t equal to 50, isn't it? So after 50, now what's in that hours, months? It's in seconds. So after 50 seconds, it stops flowing and the valve shuts off. Okay, good. So we got this answered. Okay, what else do we have to do? Give a common sense reason why the rate is negative up to this time. Okay, now remember V is the liters of water in the tank, and the water is deep because the valve is open, isn't it? So when the valve is open, what happens to the water? It's flowing out, therefore your volume of water in the tank is decreasing. So you say, since valve is opened, water is flowing out. If it's flowing out, means that volume in the tank must decrease. And because it's decreasing, must decrease. So therefore, the rate must be negative. Therefore, dV dt, the rate of change volume must be less than 0. That's the reason. So when a valve is open, water is flowing out. Therefore, you're losing volume. Therefore, the rate of change of volume must be negative because it's decreasing. All right, now we're going to integrate to find volume of water in the tank at time t. So to find the volume, we have to integrate. So write V equal to the integral of this. So when you find a quantity, we integrate the rate. Okay? And then we end up getting negative 1,500t plus 15t squared, and you have to plus c. Okay? We're going to find out what c is. So we have to use some condition in the question. So when t is 0, how much volume? It says in the question 40,000, because you say at the beginning there's 40,000 liters of water in the tank when t is 0, before the valve is open. So you go 40,000 equals to 0 plus 0 plus c. So therefore c is 40,000. And then you update your formula, so you write V equal to negative 1,500t plus 15t squared plus 40,000. Oops, didn't fit. Oh, actually, I just moved this a bit over, so it fits. Let me write this again, plus 40,000. That's your formula, which you may have to use in the second part. Okay, done. Right, good. Any question? Okay, good. So now after we do this, we can answer the second part. Have a read the second part, part D. How much water has flowed out of the tank and how much remains? All you have to do is, remember the valve gets shut off after 50 seconds. So let's find out how much water has flowed out. So when t equal to 50, let's find out V. So 50 equal, so the formula is this. negative 1500 times 50 plus 15 times 50 squared plus 40,000. Okay, let's use your calculator to do. So you do negative 1500 times by 50 plus 15 times 50 squared plus 40,000. Yes, equal this much, 2,500. Is that the answer to the question? No, remember, what does V stand for? Water in the tank. In the tank. We want to find out how much water flow out. So what do? We have to subtract. So you have to read the question very carefully. So flow out water must be 40,000 minus 2,500. That gives you the amount of water flow out. So that will be, I don't know, just use your calculator, minus 40,000, 375,000. That much water flow out. So that's actually how much remain in the tank. That one. Okay. So you have to read the context very carefully. Alright, good. So we're going to do more problem. This is called application of calculus to physical world. So you have to interpret what you found and relate to the question. We've got 3 more pages to go through. Okay, good. And then we'll do exponential growth and decay tomorrow. Alright, let's move on or finish. Alright, we'll go to the next page. Alright, next question. We have to interpret graph. The graph to the right shows the temperature of a patient suffering from Siemens syndrome at time t hours after her admission to the hospital at midnight. When did her temperature reach maximum? So remember, t is in hours, so the temperature maximum must be at 3. So after 3 hours, after midnight, in other words, that must be 3 a.m. So 3 a.m., the temperature reached its maximum. Okay, good. So when was her temperature increasing most rapidly, and when does it decrease most rapidly? All right, increasing most rapidly means when the gradient is greatest. Maximum gradient, which is the steepest. And also decreasing most rapidly means minimum gradient, or also steepest in the negative direction. Okay, let's start to do the first one. I think increasing most rapidly, maybe I think at the beginning, right? Maybe that's at 12 a.m. Whereas decreasing most rapidly corresponds to this point, like an inflection point. Inflection, usually maximum gradient occur at inflection. So can you see the gradient here is the steepest in the negative direction. So maybe after at 6 a.m. is decreasing most rapidly. All right, we answer both questions. What happened to our temperature eventually? So if you look at the graph, what's happening? It's approaching a asymptote. So we can say the temperature is reaching a stable temperature. Stable temperature. Or you can say the temperature is stabilizing. Yeah. Same thing. Temperature. Okay. So the temperature starts to stabilize after 9 a.m. Okay, it starts to reach a asymptote. Okay, and then we're going to sketch the graph of this at which the temperature is changing. So we're going to sketch the graph of derivative. So we're going to draw this. Let's try to draw the graph of derivative. So we're going to look at 3 points, so 3, 6, 9. So we'll draw this So 3, 6, 9. Okay. Now remember the gradient is 0 at 3, right? Because the gradient of tangent is 0, so you put a dot at 3, like that. And then on the left of 3 it's going up, on the right of 3 is going down, approaching a limit. Okay, good. So what you do is 0, that's maximum. Remember the gradient is minimum at 6 a.m. Okay, 6 a.m. is minimum. dt minimum. So that corresponds to the least gradient, minimum gradient for decreasing most rapidly. That's where maximum gradient for increasing most rapidly. Increase rapidly. Rapidly. And that's decrease rapidly. Rapidly. Okay, so we got this. So let's try to draw this. I think it looks like this. Okay. And then what happened after that? It's approaching 0, isn't it? The gradient is approaching 0. The temperature is stabilizing, so it stops changing. So approaching 0. Like that. That will be your graph. Okay. So it starts positive gradient, then negative gradient, and approaching 0. Right, that's your graph of derivative. Got 2 more questions to do, then we're done. Right. Alright, let's move on. You're finished? Yep. Right, all done? Okay, let's move on. Okay, next page. Another problem. We have to interpret the graph. Frog numbers were increasing in Ravnavila district, but during a long drought, the rate of increase fell and actually became negative for a few years. The rate of population growth of the frogs has been graphed to the right as a function of time t after careful observations began. When was the frog population neither increasing nor decreasing? That's the graph here. When is it increasing or neither increasing or decreasing? That's when the rate is 0, isn't it? That's when the p dt is equal to 0. And when is it 0? At 4 months and 12 months, isn't it? Years. T is in years. So after 4 years, 4 years after observation, and also 12 years after observation. Okay, good. What's the other bit? When was the frog population decreasing most rapidly? Decreasing most rapidly. How comes this? Oh no, sorry, I read the wrong one. When was the frog population decreasing and when was it increasing? Okay, it's decreasing that's when the derivative is negative. And when it's a negative, it's over here, right? So between 4 and 12 months. Between 4 and 12 months. And when it's increasing, that corresponds to this bit. So that's when the p dt is positive. That's when between 0 and 4 months and between 12 and 16 months. Years, sorry. Years. Get rid of that. Years. Years. Okay, so that will be years. Okay, so between 0 and 4 years and 12 and 16 years. 12, 16 years. Okay, good. So now we'll learn how to interpret the graph. And when was the frog population decreasing most rapidly? That's when you're looking at the minimum point. So that's this point here. So you just say after 8 months, 8 years. Okay, after 8 years is decreasing most rapidly. It's the minimum. And when during the first 12 years was the frog population at a maximum? This requires a bit of thinking. Okay, so when it was the population, frog population be maximum during the first 12 years. Okay, good. All right, so to do that is think of the frog population is increasing in the first 4 years, isn't it? Right, and after that it starts to decrease. So therefore, the maximum population must occur at 4 years, isn't it? Because it's increasing here and then decrease. So that means must be 4 years to be a maximum. 4 years. Right, does that make sense? So after 4 years, it starts to decrease. So before it decrease, must be the maximum population. Yep. Oh, yeah. So when was the decrease? Oh, no, not before decreasing most rapidly yet. So at this point, 8 years, so the gradient is the minimum. So it's decreasing most rapidly. Maybe I should say at 8 years. Maybe at 8 years. At 8 years. Yeah. Yeah. So when after 8 years, the gradient is minimum. So therefore therefore it's decreasing most rapidly because it's the least amount. Yeah. Okay. And when was the population minimum? That's when it stopped decreasing, isn't it? So it will be at this point after 12 years. Okay? After 12 years, can you see it's increasing, then decrease, then increase. So before it increases, that's the minimum population because it has been decreasing from 4 to 12. And then we're going to draw the graph. So now we have the information to draw the graph. Okay, so we'll put in 4, 8, 12, 16. 4, 8, 12, 16. Okay, so we'll do this first. And then what we do is we're going to draw the graph. Now remember, it starts to increase in the first 4 years. So we start somewhere. We don't know how many population at time 0. So we start to increase and then becomes a maximum at 4. And after that, you start to decrease. Decrease like this to a minimum at 12. And somewhere in between 8, that's when it's decreasing most rapidly. There's an inflection point. Right? So there's an inflection point that corresponds to decreasing most rapidly. And then before it starts to go up again. Right? Alright, like this. So that's your graph of P against time. So the 4 corresponds to the maximum population. The 12 corresponds to the minimum population. That's 8 corresponds to decreasing most rapidly. Decreasing most rapidly. Which corresponds to the inflection point. Okay, like that. Alright, one more question, then we're done. Example 6. Alright, when ready, go to the next page. Alright, all finished. One more page. Okay, last question. Okay, alright. In the next question, we're going to look at drought. The flow rate of water from well gradually diminishes according to this formula. So given the rate, V is the volume of megaliter water that has flowed out. So be careful. You have to read the question that V is not the water in the tank, it's the water that's in megaliters flow out. Okay? After T days. So T is in days after time 0. Okay, so we're going to look at the first question. Okay, so show dV dt is always positive. Explain the significance of this. So, remember V stands for the amount of water that flow out. And because it's flowing out, V must be, because it's flowing out, because V measures the amount of water flowed out. Therefore, it must increase. So V must increase. V must be increasing. Because the more you flow out, the more volume has water has flow out. Therefore, dV dt must be positive. Yeah, so that's the meaning of that. Okay. So it's because because V measures the amount of water that flow out, V must be increasing, therefore dV dt is positive. And we're going to find V as a function of time t. So to find V, you have to integrate the rate. Okay, integrate the rate. And to integrate that, we have to remember how to integrate exponential. You do 3 over negative 0.02 e to the power of negative 0.02 t plus c. Okay, and then use your calculator. 3 divided by 0.02, which is negative 150. Right, like that. And we have to find C. Now, how do we find C? Let's examine what happened. What's the value of V when t is 0? What will V be? Now, it's not really stating the question, so this one you have to use some common sense. Think about what does V stand for, okay? So when t is 0, what's V? Yeah, why is it 0? Because V measures the amount of water flow out, so when at the beginning, no water has flow out, isn't it? So 0 because no water has flow out yet. Has flowed out. So therefore 0. So you have to use some common sense in this to work out what V is. Okay, now we can find out what C is. So you go 0 equal to negative 150 e to the power 0 plus C. E to the power 0 is 1. Therefore C equals to 150. Okay. So you write down the formula, negative 150 e to the power negative 0.02 t plus 150. That's your formula. Okay, good. Okay, good. After we do this, we'll do the second part. How much water will flow out from the well after the first 100 days? So what you have to do is just substitute t equal to 100. So V equal to this amount times 100 plus 150. Use your calculator. So let's use your calculator. So negative 150 times shift e to the power of negative 0.02 times 100 plus 150, you will get, after 100 days, 129.7 liters of water has flowed out after 100 days. And then we're going to draw the graph for V against the time. And then t goes to infinity. Okay, good. So we describe the behavior as t goes to infinity. So what you could do is you just substitute a big number on your calculator. So you substitute 100. What if you substitute 1,000? Gets 149. Substitute even bigger, like 2,000. That's after 2,000 days, 150. So when t goes to infinity, V goes to 150 liters. Okay. And then we're going to find what percentage of the total flow comes in the first 100 days. So percentage must be 129.7 divided by 150 times 100%. Use your calculator. So you do 129.7 divided by 150 times 100. That gives you, so after 100 days, 86.47% has flowed out. Flow out in the first 100 days. And finally, we'll draw a graph of V against time. Now remember, initially there's nothing, right? 0. And after 100 days, actually there's an asymptote at 150. And about 100 days, 80% has flowed out, so it will be about 129.7 100 days, and then it just goes to this. Okay, that's the graph of V against time. So sort of we can draw the graph using the information contained in the question. There's an asymptote, and half the 100 days is 129. When t is 0, it's 0. Okay. All right, I think all done. So you can try the exercise which I'll give you from the Cambridge booklet. That's it.